this is the right solution, and this is the isolator already installed after the preamplifier. You can see two filters, receiver filter, transmitter filter, again circulator front of the amplifier. So this is the 6 centimeter. This is how looks the measuring of the SWR on my feet. You can see minus 35 dB, relatively acceptable. I can do that better around the minus 40, but 35, I was happy with that and leave it because I was hurry to test the first QSOs. So 10 gigs, I have a 31 watt SSPA. On the feed horn, I have something like 28 watts. And then 0.8 dB noise figure, dB6 NT, and a linear feed with the horizontal position. And I have one special twisted waveguide front of the feed horn, which I am turning from the horizontal to vertical position. This is my previous construction in a PVC box, but then I have a problem with the RF ingress, and I rebuilt it to the aluminum box, which you already saw. This is this new transverter in alu box with the RF detection. RF detection is here, and it's very important to know that you seriously have the RF in the antenna, not only on the indicator somewhere, some DC voltage on the coupler inside and something like this. So that I have the small horn here. I have the connection to the detector. You will see that here. It was the previous solution with the BAT 15, but it was not giving enough DC voltage. And the new system which I'm using was described by Paul, W1 gigahertz, where you have the one detector on output. You have a 1.5 volt, what is absolutely enough to see how much power you have. This is the solution. It's a RF detector LTC 5508, and here I made a graph that you can see that on a frequency 70 cents, 2313, how much is the DC output with the RF input to the detector. I have tested it. It works also. It's designed up to 7 gigs, but it works also on a 10 gigs and also on a 24 gigs. Is still giving DC around 0.6, 0.7 volt. So this is the new 19-inch rack, the portable rack, where I have built the system with the sequencer. There is a 20 dB attenuator, which is very important because I did a drilling hole to the transceiver to have the other two outputs for RX, TX. I have just only one, but it's coming through the relay, which is presented here. And in TX way, I have a 20 dB attenuator, so that if you accidentally switching full power, you have on the output maximally 1 watt, and nothing can to happen with the transverter. You never damage the transverter. So there is also the SDR. There is the micro KR shelf for the cables, and this is the space I have prepared where will be installed the other 19-inch box where will be completely the OE5 JFL controller front of you in the box. So we have the picture on the right side. This is the 20 dB attenuator which I have in the box. Important thing why I chose the ICOM 9100 is that I can use it directly on those frequencies for EME traffic, and then I can use it for the microwaves with the transvertering up to 144, and then ICOM 9100 is a possible lock internally with a 10 megahertz GPS normal and existing TCXO presented in ICOM. You can use with the 1 ppm and the GPS locket oscillator. It looks like this. It's developed by David, VK3 Hotel Zulu, small plate, just a couple of the wires, coaxial cable with 10 megahertz, and you have perfectly locked signal. With the Charlie, we were just only 12 hertz out of the scat frequency on a 3 centimeters. So that I think that 12 hertz is relatively acceptable. And how Joe explained me, it was thanks to my antenna was not pointing directly in the moon, and I was a little bit shift, so that the 12 hertz was not our mistake in units, but it was thanks to the wrong pointing of my antenna. So thank you, Joe. I was very happy. So the GPS normal 10 megahertz you can buy on eBay. Very easy. How it looks if everything is locked, so that you have indication that the GPS is locked, you have indication, and you have the 8 independent 10 megahertz outputs which you can connect for the all existing units. I am using also the GPS for time locking, very important. Then because we have not so much time, I have to be a little bit quick so that I will jump. Then SDR, measuring sun noise, of course, if you compare this, it's a 9.3 dB, so I have a 9.3 dB noise with the small antenna. I am using very smart technology. It's the spectrum analyzer, SDR spectrum analyzer from 1 hertz up to 4.4 gigahertz, which you can use combining with the tracking generator and computer, like portable spectrum analyzer. You can measure cables, you can measure preamplifiers up to 4.4 gigs. And also this tracking generator is possible to switch to the position CV generator, and with the GPS locking through the one port, you have the perfect exact signal for a test of the A.R.I. This is one picture from the SDR. I was always very surprised. This signal is via the moon, but it's SP6 JLW with 300 watt on 3 centimeters. And those all other, it's our size station with the normal standard RF power. Sun noise on 10 gigahertz. Moon noise, very important. I have now between transmitting and receiving periods, I am watching, I have a setup that my moon noise is minus 79.9, and the curve has to be around that. Otherwise, like this, it's necessary to make the correction and move the antenna back exactly to the moon position. Software WSJT10, you can see that the lines are going from down left, down right. Sorry, because this is the standard VSJT. I am recommend to use for the microwaves VSJT-X, which has the Doppler correction, and then you can see that during the whole period you have the straight lines of the signals. This is the OK1 Kilo India radio on CW. This is the couple of the pictures from the Parisian last week. You can see I had on the one wooden platform by the sauna. In this house was a sauna, so that they give me the table, chair, so that I have a very comfortable place for operation. And so here you can see 6 centimeter transverter in antenna and prepare for a moon bouncing. This is exactly the time where I was measuring the noise of the sun. Again, the picture and detail of the 6 centimeter transverter. It was the problem which I had there, because the hotel was in the big valley, and on the east and on the west I had the same hill, so that the 15 degrees in elevation, I still saw the ground noise, and I didn't see the horizon, so that I was very, very much limited, and I was able to be QRV only 6 hours for every period. This is how I had built the working place. Very nice. I told you in this left side was the sauna. I had a table, I had the chairs, we had a fresh beer, we had everything what you need for the expedition. So a couple of the QSOs. This is my very happy QSO. I have to tell you why, because I am active as a ham radio from a year 1972, and it was my first QSO on 6 centimeters ever. I never touched the 6 centimeter before, so that I was so happy. At first it was via the moon, and second it was on a 6 centimeter, and third it was with the DAN HB9Q, so that you can see we work it very easy. Report you can see on the left, report which I got from a DAN you can see on the right. This is the QSO which I made with, it was the random with the UA3 PTW with Dima. I was calling CQ, and then Dima was calling me back with the very nice signal, minus 16 dB, minus 15, no problem to decode with the very, very bad conditions. Then on 3 centimeters, I work at Tolly. Tolly is sitting here. Tolly, thank you very much that you were there. And also, OK, 1 kilo India radio. We made a lot of the tests and find some the possibilities, problems, and again, things which is necessary to do in the future. And here you can see the picture, how big was the spread, 180 hertz. So this is the signal, OK, 1 kilo India radio. So guys, thank you very much for your attention. I have to apologize, I am 4 minutes over the time, but we start a little bit later, so that I hope that you can apologize. Thanks very much.
So any question? Please. 1 second.
Yes. Yeah. Here we are. Thank you very much.
Okay, let's go for a picture. Fox 6 BKD. Fox 6 BKD, you said about the mesh. What is the mesh aperture, please?
It was 6.6 millimeter, and it was welded, and how to say it? It was with the zinc anti-corrosion protection.
Okay, thank you.
Al?
1 second, please.
Sorry, I don't hear you.
Real loud.
Okay.
What is your plans in terms of 3 centimeters? Are you going to go circular or linear?
This is a good question. You know that in 2002 on the Prague conference, we decided to use all frequencies over the 70 cents circular. It was also the reason why I spent so much time with the septum feed. I have already septum feed for a 3 centimeter with 2 waveguide outputs. One is connected directly to the SSPA, second goes through the waveguide switch to the LNA. It works, but now, let's say 90% stations is a QRV with the linear polarization, and I don't want to lose the 3 dB comparing with the linear. If everybody will be circular, okay, then it's without the problem. I am ready to go, and I can do that. I don't have a problem with this. Any other question? No, thank you very much again.
So, he's very tall, actually. So next presentation will be from Guy, F2CT, PB8, 13 meters, Cassegrain Dish Adventure with ORPB Society.
which is located in near Lannion. Some of you were present in 2014 at the EME conference. So it's a short movie.
You need the movie?
Yeah. Yeah.
Tell you what's happened if you hit the Copernicus crater with your
You will listen.
I think that's a problem with the decoder. Give me 2 minutes, I'll download a new software.
It's run with VLC. Sorry.
trafic avec Swan Delta Bravo, Fox 2 Charlie Tango, 73 numéro Willy, très heureux de t'entendre en SSB, là c'est très très fort. Des amitiés numéro, tu as les amitiés de Lucien également, Fox 3 Mike Echo. On trafiquera demain avec son indicatif également. On trafiquera demain avec son indicatif Fox 3 Mike Echo. 73 Willy, 73, à demain j'espère également, et à très bientôt sur notre bande. NX1 Delta Bravo, Florida 2, Charlie Tango avec nos amitiés Willy, Davida. Sur Max.
Okay, you can move to the file. So it's not an amateur station, okay, but we are several AMs who work very, very hard to get these results. It was very, very difficult because we are not the owners of the big dish. This big dish is the property of the local authorities, and we rent only the location. So I would like to share you with my own experience with the ORPB Society, which was created in 2009. It was created with the old technician and engineer from France Telecom Center, which was the special center for telecommunication, who moved now to Bercenay in the east part of France. So some friends would like to keep the location with some big dish, and we have spent many time and a lot of money to improve this dish, which was only used on C-band for satellite communication. So when I was a young engineer, my dream was to use this big dish in Lannion, and the dream was achieved in 2012 because they asked, the staff from ORPB asked me if I was able to improve the system and to use it on the EME traffic. So this challenge was very hard, and we need the help from engineers, also from AMS, such Jean-Marc F1 HDI, Jean-Jacques F1 EHM, and some others. So the goal, it's to speeding. You have to please to go back. With that? Okay, sorry. So in 2012, the ORPB would like to participate to the anniversary of the first TV transmission between France, stateside, and Great Britain, and which took place on July 10th, 1962, with the Telstar satellite. So the challenge was to modify the equipment of the PB8 to be possible to use it on 6 centimeter. So I bring my equipment on the PB8 location, and after some measurements, some tests on the 6 centimeter original feed on and all this system, you will see that besides the feed on, there is a lot of equipment, quadplexer, and some receiving system also on 4 GHz, and we can use the 4 GHz band to see the moon noise, even in transmitting system. So it was very, very interesting. So on July 9th, we received the first echo from the moon. Sorry, I think it's an over file. Yes, it's here. How I can choose the echoes? No. Before. There's some records, and I would like to listen to echoes.
Allô la Terre, ici la Lune.
So.
Allô la Lune, ici la Terre. Over, over.
It was the first echo. I was speaking to moon people, but fortunately nobody.
Allô la Lune, ici la Terre. Allô la Lune, ici la Terre. Over, over.
Okay. So yeah,
Tango Mexico 8, Papa Bravo. Tango Mike 8,
you can
Papa
stop.
Bravo.
Okay. You can
Tango
stop.
Mike 8, Papa Bravo. Texas Mexico 8, Papa Bravo. Over, over.
Okay. So it's the first echoes in SSB we got with the PB8 system without any modification. Only I received a phone call from Willie Alex 1DB because during the presentation with a lot of people, and we make some demonstration with the moon echoes, and Willie said me, "But Guy, you are on the wrong polarization, because on just beside the feed horn there is a very big switch, and unfortunately if we don't power supply the switch inverts the polarization." So when Willie have a phone call to me, I went into the plenum and modify the two cable for receiving in RHCP and transmitting in LHCP. It was a first improvement. So during 1 year, we work on the tracking system. As you know, this big dish was only designed for satellite, for stationary satellite, and not for tracking the moon. So the goal was to modify the tracking system with very accurate, with 1,000 of degrees. But we need a special software to move the dish in azimuth and elevation. So Jean-Marc F1 AGI help us to make a small software to modify. So you have the mechanical characteristic of the feed system on 5.7. It's very big. The subreflector weight is around 400 kilograms. And firstly, we would like to modify the feed system to use PB8 on 10 and 24 gigs. But unfortunately, it was impossible to put down the subreflector, and yes. And you see the feed on here, and all just beside the, oh, sorry. From this part to the feed on to the plenum, there is a lot of electronic system with the quadruplexer and switch guide on WR137. So it's impossible to dismantle all that system. If we dismantle that, we will not able to use the PB8 because all is waterproof and so on. So we decide with the help of Jean-Pierre Blanc, who was an engineer from French Telecom, to try to put on the PB8 on 10 gigs. So Jean-Pierre Blanc designed the 10 gigs, the 3 centimeter feed on, with a setup from OM6AA, and it was built P1 RKI. We made it with at a reasonable price. So the design of the feed-on here with a lot of simulation. On 10 cheeks, we expected around 59 dB of gain. On 6 centimeters PB8 have a gain of 57 dB. Yeah, thank you. Sorry. And on the aperture on 6 centimeter is 0.235 degrees. On 10, 0.137, and on 24 jigs, 0.07 degrees. So we must work on the tracking system hardly. So we made a lot of tests on sun noise, moon noise, and the efficiency was a little less than expected. On 6 centimeters, the efficiency is around 75%. On 10 gigs, we have only 46%, and 24 gigs, only 28%. But it's worked. So, is a design for the 24 feed made by PA1 RKI with a simulation from Jean-Pierre Blot, the engineer. And you see here the gain expected of 62 dB on 24 gigs. Here the f-stroke of the PB8 is 0.27, but we cannot use it on prime focus design. Well, we can only use it on Cassegrain, and the improvement for 23 and 13 centimeter and from a radio astronomy will be also on another system to illuminate the PB8. So we have some echoes, some code echoes. After. You can move to K1JT, CW. It was on 6 centimeter. LX1DB, you can move. This is K1JT. You can move to LX1DB. use the audio file here or not? This is Gerald K5 Golf Whiskey. Sorry. So you listen to the signal strength. Sorry, but the quality of the audio quality is not good because we made the record in the shack. So sorry. Hello. It's not. Yeah. Yeah. No, sorry about the audio files. It was not a good quality because we record into the shack, not directly from the receiver. So I will put all the records on the special key, and you will have lot and lot of echoes and signal from everybody, from RK to UIH also was very, very loud. So these pictures show the accuracy we get in 2015 during the activity weekend on 24 gigs. You know, you see the target here, and the 0.008 degree, and we get 0.3 on Azimuth and 0.015. The target was 0.2. So we after long hard work by the a digital engineer, we arrived to get a good quality, and to this make possible to use PB8 on 24 gigs. So this is the plenum, just under the dish. So you can see it was the 6 centimeter transmitter here, a rotative joint here, and the two feet vertical and right hand and left hand circular polarization from the WR 137. Only 6 meters of waveguide, and I connect my transmitter just here with a 2 transition between WR 137 and connectors. I'm running around 60 watts here, and 0.6 dB of noise figure. So it was a visitor. I don't know him. I don't know why is he here, but So the goal now is to use PB8 on radio astronomy on band L and the band S, but we have a lot of work to modify, and I would like to thank Al, also K2UH, when he went in 2014, he gave us some good ideas to use PB8 on overbands and to keep the C-band system now. So this is a check. My own computer. This is a FT. Don't smile. It's on a single FT8 817. We're using in transmitting with all the data with power and so on. This is a K3 with Doppler compensation with a small 432 to 28 megahertz converter. All the it's a technical local. You know, this is the F2CT, a technician from French Telecom, Pierre-François BQP, which is here, and me operating the system. Okay, so some question about the result. I have some files. If you want, I can make some. I made some recalls on 10 gigs and also on 24 gigs. You will see the.
Hello.
Sir, une question.
Une question, monsieur. Guy, when are these beacons likely to come on? What sort of time scale for the 6 and 10 gigahertz beacons?
Oh, yes, I forgot it. Sorry. In 2015, we get a special call sign for KGM, which is a radio club call sign, and we will use it for drive the 6 centimeter beacon. So 6 centimeter beacon is in preparation by the ORPB staff. I give us the pilot, the power amplifier, and so on. Is operating get around 20 watts, and I think they will be able to get 50 watts. So now all the electronical and electrical command on the PB8 are dismantled, and the ORPB is rebuilt all the system for security and so on. So I think in about 1 or 2 months all will be okay, and the F4 KGM beacon will start.
And will it be on 24/7 or just whenever there's stuff?
No.
No.
Only on demand.
Okay.
The beacon keeper is a Sylvain F6 DBI, so it will be like a DL0 SHF on 10 gigs.
Right.
We will activate it only on demand because of security of the system. Okay.
Okay. Thank you.
So, and also on 10 gigs, I get a special call sign at 5 Zulu India Fox for the 10 gigs beacon. And we prepare all the system, and we'll be operating also on 10 gigs, on a 188 also. Okay.
Can do the SSB files. I got them.
Okay. So last thing, we have some good recalls on 10 gigs. OZ1 LPR, for example, yes. So when we were QRV on, sorry. So it's OZ1 LPR in SSB on 10 gigs. So on 10 gigs, we are using only circular polarization due to mechanical restriction. So we cannot use linear polarization. So when we will work you during the bus or RRL contest, we were in circular polarization. And on 24 gigs, I have some screenshot. Unfortunately, I don't know if I have some record. I think that Willy LX1DB record us in SSB on 24 gigs, and we expected to get around 20 watts at feed. Unfortunately, due to a coax cable failure, we have only 1.8 watts at the feed. So we made some QSO on 24 with only 1.8 watts. We work also Andre F1P wire on SSB on 10 gigs, and it will be the next goal to be QRV again on 24 gigs perhaps in the October or November. So I have two screenshots from a JA4BLC on 24 gigs. It was amazing with about the result with only 1.8 watts. And now we know that we can use PB8 on 24 gigs. All the engineer who was working on the site on the CTS said us that it was impossible to use PP8 on up to so you know, with the it was a signal at JA4BLC. Have the second one, please. Yeah. Okay. We made a lot of before the activity weekend. We made a lot of tests on sun noise and moon noise. The moon noise, the reliability is okay. We get around 1.8 to 2.1 dB, and we don't explain why on Friday we get more than 20 dB of sun noise. We don't know why, but it was reality because we measure the noise figure on the spectrum analyzer on all the bands, and it was the real value. So we don't know why. Thank you very much. For those who can go to Lannion, near Lannion, well, welcome. PB8 is open for all of us, of you. You can use it if you want to make USO or measurement on sun, moon noise, and so on. So there is a City of Telecom, a Museum of Telecom, and every AMS must visit this wonderful location. So thank you very much.
Thank you, Guy. Thank you very much. I will make a copy of the files.
Yeah, you can. You can.
Okay. The digital part. Okay, so it's really, I've been there 2 years ago. It really is worthwhile to pay a visit to Plemer Bordeaux. I liked it very much. We go on now with, here we are. Charlie, G3WDG, experiences with circular polarization on 10 gigahertz.
Is that right, or
I think that it goes more or less like sunglasses. So. turn it around. Yeah, that's Where is it? No, your mouth is definitely not there, but we'll try to squeeze it a little bit. Maybe. So you have a big head, actually.
Okay.
Leave it here. It will
Okay.
work.
And slide, that's... Right, I'd like to share with you some recent experiences with circular polarization on 10 gigahertz. And I would like to thank very much OK1KR Group, LX1DB, HB9Q and SM6F8Z for their useful participation in these tests and general comments. This was a set of tests that we organized and had a lot of people all trying to work together on it. Okay. So, what I'd like to talk about today are my own expectations for circular polarization. There's been a lot of standards, a lot written about it, so you get an impression of what it's going to offer. Testing a feed horn, a few new things I tried to do whilst developing, making a horn and then testing it. How to try and check the circularity. Developing some test software for measuring signal-to-noise ratios of my own echoes. And then some comparisons of linear polarization to linear polarization and circular to circular on own echoes, and comparing circular to circular and linear to circular with LX1DB. I hope it will become a bit clearer as we go on. So what were my initial expectations for circular? That it would have the same signal levels as circular to circular as linear to linear would. So there was going to be no penalties in going circular. To when working stations with linear polarization, we were going to lose 3 dB. There had been something in the literature about circular polarization having narrower signals than linear. And I wanted to test this because for digital communications, the narrower the signal bandwidth is from the libration spreading, then effectively you get better decoding. So there was a lot of interest to see whether it would have some advantage. Another expectation was that since circular had been in use for quite a few years now on 3 centimeters, that everybody would be on the same sense. And also the expectation was that circular polarization feeds are not as easy to build as linear, but we thought we'd try. So I cut out some slides. They're in the presentation on actually building a feed horn, but the article was in Dubus and there is some photographs in the digest. Testing feed horns is however general. This isn't just applies to 3 centimeters. This also applies to any band where you build a CP feed. I was using the SM6F8Z 0.692 wavelength feed. This one was ideally suited to the F to D ratio of the dish, had good predicted performance, and so I opted for that one. So lab measurements that you can easily do is return loss on one of the ports and isolation through from the transmit port to the receive port. So the feed into the open air, you have isolation in yellow, so we're getting an isolation something like 25, 27 dB, and a return loss of about 28. Good enough. Don't need 56. Put it in the dish, it'll be different anyway. So didn't spend too long working to optimize that, just wanted to get it close and good enough. These plots are from 10 to 11 on a 10 dB per division scale. The interesting thing was trying to measure almost the conversion of right to left hand. In other words, the isolation or the axial ratio of the feed, trying to measure it this way, was to short the feed out. Now, because the sense of circular when hitting a reflection reverses, then if the feed is working well, and if you have a good axial ratio, then the signal should start off from one port, hit the reflection, and then the reflected power should be in the opposite sense of circular and should come out of the other port. And this actually works. The isolation that was over here, 24 dB, is now almost 0, 0.3, and the return loss doesn't change very much. Again, showing very little power comes back in the same sense. So this looked like the feed horn was working well just from a simple lab test and shorting the feed out. Trying to measure axial ratio in the lab where you have lots of reflections is very difficult, and you just get, you know, hard answers, difficult answers, difficult to interpret. So it looked like it was working, but nothing like an on-air test. So we teamed up with the OK1 KIR group. Now they run rotatable linear, so they can rotate their linear polarization from the shack. And each data point here was 48 seconds of JT carrier. We were recording the wave files, playing them back later, and analyzing the signal to noise ratio. So this total test took 38 minutes to do. And with a little bit of variation in tracking, it's not possible to get a perfect result, but broadly speaking, I think we're within plus or minus 1 dB circularity, worst case, probably a little bit better. So that tended to verify the short circuit plate method for measuring it. Now moving on, what was the real motivation here was to see, is it true, all these expectations of circular true? So this is beginning to start the comparison of linear and circular. And my first attempt was quite a crude one, really, quite simple, was to use own echoes and WSJT fast modes. So you can actually, using JT9, you can actually get your own echo back and decode it in, I think it's a 1.7 second message length for one of the modes. And these are messages, so this is transmitting, and then the echo back. So this is all done in like every time you transmit, you can get an echo if it's working. And just to show, if you reduce power, these are the transmitted, and you've only got two out of 6. Here we got 6 out of 6 decodes. The results were very difficult to interpret, rather variable. Again, had there been a narrower signal and an equal level signal, then circular and linear should give the same answers. But it turned out to be quite difficult to unpick what was happening. What did show up, however, was the JTMSK, which requires a high degree of coherence to get, you're almost using the whole bandwidth of the echo, which all has to be in phase to get a decode. So that's a very critical one to get echoes with. That seemed to show the linear was better. So I didn't believe that at the time and blamed clouds passing in front of the moon and all sorts of stuff, but decided then it was necessary to write some software to actually measure signal to noise ratios accurately. If we were going to get a good handle on what happens with linear compared to circular, we needed to get some accurate data. So I wrote a little program in MATLAB which basically mirrors the echo mode in WSJTX. Couple of modifications in that I have a log plot instead of, I have a linear plot of each individual echo and a log plot of accumulated echoes. So if you keep collecting it, you keep getting echoes, then this reduces the noise level and gives you a better, you can make a better estimate of the signal to noise. Doppler control, of course, is very important because every echo has to come back exactly on the same frequency. Having an IC735 with 10 Hertz steps is not good enough for this kind of echo testing. There's too much spread in the frequency of the return. So I was using here Mirec OK2AQ's software, which can set to 1 Hertz instead of 10. And this is driven by WSJTX's, does the calculations. This program picks up the numbers and then tunes the local oscillator. And I spent some time trying to verify this works. So is it accurate? Obviously, if you're going to start trying to say linear is better than circular or the other way around, you want to have some confidence that the results are true. So looking at what I did was varied transmitter power with the power meter, monitoring my output. And with a 3 dB drop, I was measuring echoes to within 0.2 of this 3 dB drop. 17 dB drop, I was still measuring accuracy to 0.3. And even down to 23 dB, this is with 500 milliwatts output power, it was still getting the right results to within half a dB. So I think the numbers are reasonably good. And the other thing I'd just point out whilst it's on screen is you do have a real-time display of the width of the signal from WSJTX, and that we need that for later. So next thing was testing the sense of CP signals. Everybody should be correct by now, right? Okay. So what I did was, here's the back of the feed horn. This is actually the horn. It's got a receive port and a transmit port. And so here we have the waveguide relay that's normally used for preamp protection. But instead of running a load, I coupled the other port back to the transmit port. So here's the preamp, and the waveguide switch basically switches you between the receive and the transmit ports of the feed. And thus, in running this from the shack, I can just flip it and then look at my left and my right hand polarizations and see what it looks like. There is there's a higher loss here. There's a half a dB in this semi-rigid cable on the transmit, so that means the signals I receive on the transmit port are actually strong, or half attenuated by about a dB in sensitivity because of this half dB loss. So first test was with HB9Q, and we started out, nice signal on the receive port, yeah, pretty good. Switch to the transmit port, oh, it's stronger. So, puzzle, why is this? And the same, about a 6 dB difference between 6.5 dB difference. These are the plots of the signal from the program. These were the waterfalls at the time, so you can see the stronger signal's got some nice red in it and is reflected in the stronger spectrum. And about a 6.5 dB difference in level between the two, but more importantly, it was stronger on transmit port. So somebody's got their circular the wrong way round. Of course, I was the new boy on with circular, so it's probably initially my fault, right? So, sorry, Dan. So we went and did a test with Willie, LX1DB, who's been running circular for many years as an option on 10 gigs. And on the receive port, good, it's actually correct. So it showed now we had 14.2 dB signal to noise on the receive port and 5.2 on the transmit. So now we've got about 8 dB difference between right and left hand. It wasn't infinite. That's another point with circular, is it was not completely not there on the wrong sense. There's still plenty of signal. This is why, with a good system and digital, you can, this 8 dB or 6 dB that you've lost, you may not notice it with good systems these days, but it was there. So just a quick refresh. I like to remember this by, if you think of the septum as a set of stairs, look in the front, climb the stairs, the receive is on the right. It's okay for English where right and receive are the same letter of the alphabet, but that's the point. And there can be confusion because if you label the feeds with the polarization, you've got to remember that when it goes in the dish, it's reversed. And I think this is sometimes the confusion, is if a manufacturer gives you a feed and it's got RHCP and LHCP written on it, do you mean the feed or do you mean when it's gone into the dish? And I think that's where some of the confusion can arise. And it doesn't matter whether whether these are probes or waveguides, it's which side of the septum the signal comes in. It can be coming in a hole in the side from a waveguide or a waveguide coming in from the back. However it's fed, it's always which side of the septum is which sense of circular. So okay, feed was all right after all this. Now let's get on with trying to do some measurements of comparison. So I built another feed, which is identical to the circular one, but this one has waveguide coming in the back. The idea is the size of the waveguide, the choke are identical. The assumption is these two feeds have the same pattern, and thus the dish has the same performance. That's an assumption, but that was what I tried to do. So we did several tests around the March 16 perigee. I took echoes from about 15 degrees to 35. Transmit power was always about 80 watts at the feed, and as I said, the two feeds are nominally identical. And one day I would start getting some echoes with circular, and then as the libration changed, when the libration for that day reached a minimum, we'd run down the dish, swap the feeds from linear to circular, then keep going until we hit the elevation limit. So, and then the next day we'd swap. So everybody got a chance, for either minimum absorption. I tried to mix it so there wasn't any effect there. Weather was reasonably constant from day to day, so the belief was, there wasn't any great weather-induced variations. And from a link budget point of view, the circular system had 0.3 dB advantage. I had some feed loss on transmit in linear, which I didn't have on circular. Circular had the waveguide SMA transition on the horn, so that costs you a little bit of loss. But all in all, 0.3 advantage for the CP system, so we should get better signals on circular, I thought. So this was the results of quite a few days of different tests on linear and circular. And the plot is signal to noise ratio as outputted by the program versus spreading. The spreading is the WSJT figure straight off the Astro window, which represents the total spreading that you can have. The actual spreading that matters is a bit less, but this is the total, so provided just use the same definition all the time. And what we see immediately is that from day to day, the reported signal to noise goes down as the signal gets wider. This is what we experience. The decoding is more successful when signals are narrower. You can have lower transmit power. Everything is, the narrower the signal, the better from copying point of view. But it also says that if you carry out a measurement on one day and then swap feeds and do a test the next day, the libration from one day might be 20, the next day might be 60. And so you get a huge error in the measurement because just simply the spreading is different. So if you want to do comparisons, you have to kind of normalize to the libration spreading. The other finding, immediately you can see from the graph, this black line here is circular polarization, and these all points are all linear. So at a given spreading, the linear is winning over circular. And looking at 8 separate tests over several days, my average measurement was 1.3 dB better for linear compared to circular. And since the circular should be 0.3 dB better, the difference is more like 1.6. So I think the first question that was answered, I expected CP to be the same as linear, and it wasn't. It was lower level. Now, as I said earlier, it's one of the advantages with CP, or that people have stated in the literature, is the signals are narrower. If so, this would give you an advantage. So I looked at this next, and there's more plots in the digest, but this, what I was doing was recording 16 echoes in sequence, and the software was storing me a JPEG of every echo and also an Excel data, so we could go back and analyze them. But in 16 echoes, one after the next, you see a tremendous difference in the quality. Like an echo could be really narrow, or the next echo in the sequence could be much wider. So it's actually quite difficult to say linear to circular on individual echoes whether one is better than the other. And I did a lot of tests over many different values of spreading. Again, no real conclusion. A little easier to see on the log plots. So this is all echoes added together, all these 16 added together, and I can't tell, at least by eye, any significant difference in the shapes. One thing that is interesting is that you do see a narrower signal in the center, and this is like the full width of the signal as predicted, but if you're only decoding the strongest part of the signals actually look quite a bit narrower than the total predicted spreading. So when you're trying to do simulations of digital signals particularly, the width is not, at least at 10 gigs, the width is not the total, it's less than that. So then we looked at, I did some tests with Willie now to, he was using linear, I was using right and left hand circular. So if things are right, there should be, first thing is I should receive him at the same level on right and left, was expected. If he was transmitting linear and I was listening on right and left, it should be the same level. And it should also be 3 dB down on if we had been circular to circular. Well, I'm sure you remembered on 5 slides back, this figure was 14.2 for circular to circular. Circular to linear, it was 12.3. That's only 2 dB down on the circular to circular case. So, and the other thing is, on the other sense, 11 was measured on the other port, but because of this sensitivity difference, the measured 11 is actually 12. So the measurement gives 12 dB signal to noise when you are doing linear to circular, and we measured 14 circular to circular. So I think the evidence is pretty reasonable that there's only a 2 dB drop going from linear to circular. Talking to Willie about this, he confirmed that he had seen similar results in the past. So I was quite happy to hear that he'd also seen the same effect, and that his feed horns also have about the same apertures. So I think that's also a reasonable. We weren't getting a difference because of different feed illumination, which would have, not been a fair test. Now, why is circular not performing as well as it should at 10 gigs? And I think the reason, and if you actually go back to the literature and read it more carefully, there was a paper by OM6AA, and Vlada of the OK1KIR group had actually done some calculations of depolarization. And what this showed is that for dishes of the kind of size that we use, below 4 meters diameter on 10 gigs, there is about, now where's the graph, 6 dB, 6.5 dB of ratio between right and left. So it actually is what we're seeing. I think 6.5 with Dan, 8 dB with Willie, somewhere in that region is the right to left difference. So that's saying power is being wasted somewhere, because if it's not all coming back on the opposite sense of circular, where is it gone? And it's probably gone into maybe some other linear components, which is why we only get a 2 dB drop from circular to linear. But it certainly doesn't come back on the other sense exactly, not on 10 gigs. So we also did some experiments which I have not presented, but we did another set of tests with OK1KIR where we both ran linear polarization, and with linear you see about 10 to 11 dB of cross-polar on 10 gigs. So even that, with good systems, you can work, at least on digital modes, with 10 dB of loss. Which explains why everybody seems to be able to work everybody on digital, whatever the polarization is doing, more or less. So, but it's 10 or 11 dB and not 7 or 8. So with linear to linear, there is less polarization going into the vertical from a horizontal stimulus. So that tends to back up the difference with circular. So to come to a conclusion, the measurements suggest that circular to circular work is 1.6 dB worse than linear to linear. Circular to linear has only 2 dB loss. So if you're working a station who is on circular and you want to use linear, you're not going to lose 3 dB, you'll only lose 2. We see no observed difference in spectral width between circular and linear. Of course, circular polarization does overcome the spatial loss. So this is its advantage. I mean, this is why people are interested in circular, why everybody's wanted standards that says it's all circular, is to allow for the spatial offset. But if you're after ultimate performance, linear to linear, then linear to linear will offer you ultimately a more marginal QSO than you will if you're running circular to circular. And, the circular feeds are either quite a lot of work to make or quite a lot of money to buy. So if you like, there's an entry fee to be paid if you want to go on circular polarization on 10 gigs. If you're a station with a small dish and want to get on the band, the temptation is to go with linear. And you know, a lot of larger size stations are there and will support you with that if that's what you'd like to start or stay with on 10 gigs. Al's has started a discussion in the newsletter last month about what, you know, hey guys, we're all supposed to be on circular, what's all this linear stuff? Well, this is some of what's behind that. If you are running linear, of course, it's nice. On 10 gigs, there's no Faraday, but there is a lot of spatial. So this feed actually has a proper bearing. So you can rotate linear. If you do it fast enough, you'll generate circular. But you can rotate this probably with a small windscreen type wiper motor. And have polarization adjustable from the shack. And if to aid you, the WSJTX program and WSJT10 have a printout of DPOL, which is if you have the station entered in the DX box and your own call set correctly and the grid locators, it will tell you what the linear polarization offset is. We need to have a discussion about whether you're standing behind the dish, you rotate the feed to the left or the right, but other than that, it's very clear. It's, figure it out and that's the definition. It's 26 degrees one way or the other. It is at the moment, but we'll do some tests with that. Of course, for contest activity days where you've got many stations on the band from all parts of the world at once and you don't want to be bothered with circular, with spatial offsets, then CP has its advantage. So thank you for your attention.
One second. We have a question, please.
I occasionally run linear on 1296 because there's a lot of people come on with Yagi, so I'll put a linear feed in. And if you take a note, looking at your feed, negative is counterclockwise. Hopefully I got this right because I'm dyslexic. I reverse a lot. As probably people have seen in my newsletter with call letters and stuff. But as I remember it, negative is looking, this is looking, you know, back toward your feed, okay, from the center of your dish. Negative on the programs is going to be counterclockwise, and positive is going to be clockwise, okay? Someone may be able to verify that.
So you stand behind the dish and look at the moon.
Feed. I keep a little diagram to remind
Negative
myself.
is anti-clockwise.
Right.
We'll try it.
Okay, the other point, I guess, since I have the microphone now, is it seems like you're arguing that there might be a very good reason if you want to play with circular. It sounds like with most of the people are running linear, right? You're saying that you're only going to lose 0.4 of a dB working a station that has linear versus working linear to linear. Or am I missing something here?
Okay, if you are circular,
right, circular to circular, I should say.
Yes, if you're circular to circular, I claim you'll lose for two stations running circular one end, circular the other. If they were to switch to linear, both of them, they would win 1.6.
But if everyone's on linear, you put a circular feed in, you're gonna
only lose 2.
No, you're going to lose. It seems like if you're working them, you're losing 2 dB, right? But if you're working circular to linear, it's 1.6 dB.
I'll have to think about that.
There's a 0.4 of a dB difference, right?
I think the message really is it depends what you want to do with it, and you know the idea of a common standard is great, but it doesn't meet all the needs. So when you see occasional pleas, why don't we all go circular? Well, you know, this is trying to give a little bit of more discussion.
I was just going to make a minor point, which is that we have just once again proved the theorem that to do the calculation is easier than to get the sign right.
Thanks, Joe. Yeah. Okay, there's one, yeah.
Congratulations. Thanks very much. And one simple but probably silly question I have, which is, in that set of measurements that you did with the help of Willy and X1DP, did you take into account the moon to be a perfect mirror, or do you think that the roughness of the moon might, of the surface of the moon rather, would influence the results?
I think the tests were experimental, so they are what they are. And I think, yes, the moon is rough, and there have been some papers on people measuring depolarization against different size rocks and stuff, trying to measure what comes back from circular compared right and left discrimination. And it does seem to be sort of proof that the rough surface has got something to do with it. Angles of reflection, whether it's reflection, scattering, or a mixture. You know, the physics of this is a bit outside my realm, but I think it's a combination of scattering and reflection, or multiple reflections, that are distorting. You know, there's another interesting paper I read once talking about circular, and that was in petal dishes, where, and the argument in this was that for the reflection of a circular signal in the surface that's doing the reflecting, you have to have a circular current. And if you have a petal dish without the metal making perfect contact at those edges, the circular doesn't come back properly. There is also some depolarization in dishes because, again, angles of geometry, but the paper by OM6AA is pretty clear that that's like 27 dB down compared to the moon. So it all seems to be the moon. And I think the fact that at lower frequencies, there hasn't been any real observation of this kind of effect. And there are some papers that say at 24 gigs, the depolarization is a lot worse. I think at 10 gigs is a transition band between, you know, more or less perfect 3 dBs from circular to linear and no difference between circular to circular and linear to linear. At 10 gigs, we're starting to see a difference between, you know, a degradation, if you like, is just starting to happen. Sorry,
when you use circular and listen to the wrong polarization, you are 6 dB weaker. But isn't the signal also about twice as wide?
No.
Because I looked at this paper, it looks like that.
No, the signal
The width is the same, you say?
The width's the same.
Okay, thank you.
Yeah, when we looked at the cross-polar signals, the widths are the same. Zdenek?
Just only one comment. There is the problem if you have the feed horn with the septum, which is connected to the waveguide with the waveguide or with the SMA connector. You know that I played a lot with these septums, and I can say from my private experience that the build of feed horn, circular feed horn for a 6 centimeter is a little bit much complicated, like for a 9. And absolutely simple is for 23, and for 3 centimeters, it's on the critical how to say it, it's very critical if you have the SMA connector, because if you don't have the properly installed or made the dipoles, which are connected inside in the waveguide, then you have the much bigger loss, like if you have the just only linear polarization. And the waveguide connected together for a right hand and left hand circular polarization are not easy to do, because you need to have the 90-degree angle. It has to be perfectly done and mechanically very complicated. I saw, probably we can see that Hubert has here the solution with two waveguides. Both of them are straight. I have at home, one is the straight, one is with the 90 degrees angle for the SSPA, and on the one flat of the waveguide, I have the waveguide switch, and then I have the LNA, because there is, again, if you put there SMA, the losses are much worse, like if you are using just only linear polarization.
Sure. Yeah, I really built an SMA horn because I didn't think I had the skill to build one in waveguide. The SM6FHZ looked possible to make at home, but I do accept there is a performance degradation due to the use of the SMA connectors. But I see slightly lower sun noise, I see slightly lower moon noise with circular, but that I attribute exactly to the losses. But for the measurements, I think I've taken that into account as best I could. Thanks, Zdenek.
Last question, then we'll have our break.
I was just going to point out that in Europe, where you're all close together, the polarization loss is not that great, because you're going to track together. But someone who's operated 10 gigs linear in the States, it surprised me how rapidly the depolarization comes up. It is, unless you're, and I was not set up the way I can mechanically rotate in some cases my pole, but that means I got to go down, I got to jump, get up to my feed, move it. You're doing regular operations to correct every couple hours. Your polarization is very awkward, and you start losing a dB very quickly. I used to think, oh no, it's not important, but if you're making comparisons and comparing 1.6 dB versus what happens, this dipole it's something we need to think about.
Yeah, definitely.
Thank you, Charlie.
Thank you very much.
This is for you.
Perfect.
And,
Thanks.
thanks again. I didn't want to interrupt the iterations, since there
Okay.
were many useful
Yeah.
questions. So we'll take a break now, and we resume in half an hour with the following talk about techniques used in a construction of a homebrew 10 meters parabolic antenna by Chris, VK5MC. Enjoy your coffee break.
And even if it's full cross-polarization, you see
little bit, that's enough. Yeah.
Make no picture.
we are ready. Let's see if everyone else is realizing finally that, yeah. Oh, by the way, we have our big man here for the raffle tickets, so he has a nice box there. No, by contract we can't. Everyone else is realizing finally. By the way, we have our big man here for the raffle tickets, so he has a nice box there. Okay, so we have another two presentations, and I wanted to give you another piece of information. Okay, we'll have two plus two coaches departing for the gala dinner tonight. First two coaches will depart at 19:30. And 15 minutes later, so at 19:45, the other two coaches will depart. So don't wait for the last two. Okay. After the last presentation, I suggest we go outside and do the customary group photo. Because as far as I know, some of you will not be present tomorrow, so better to do that today. So I'll give word to VK5MC Chris. Thank you, Chris.
G'day. It's good to be back with friends. Firstly, I'd like to give an invitation to any EME amateurs that visit Australia to call in and see me. There's not many EME hams in Australia. I'm trying to promote them, but it's good to see overseas visitors if they do get to VK. Okay? And firstly, this is not look what I've done production. It's look what you might be able to do to firstly make accessing your feed much easier without running the risk of falling off, as some of the hams over here have done. And the other thing that people seem to do, they make a dish and the structure of the hub assembly is weak, and if you get a breeze, the whole system bends and you lose your performance. So, music. Which one am I meant to press? No? Okay. This is an old dish which I put together after the death of a friend of mine, Ron VK3 AKC, used this particular dish in Geelong back in the 70s. After his passing, it came over to me and I put it together. And as you can perhaps see, it's got a few faults. If I had to work on the feed, whoops, wrong way. Wrong button. I had to work on the feed. I had to put a ladder up and climb up there to access the feed. Not good. You can see it's probably lost its shape a little bit because the hub was only made out of inch aluminium tube. It wasn't strong enough by any means. The other problem with it, it was BC, before computers. So the only means of telling where it was pointing was some Selson motors. And Selson motors and computers don't really match up together. So this gave me a foundation of what not to do when I built a bigger one. So my design factors: strength of the hub to hold and grab. When you build a dish, you've got to grab it with something. The hub's got to be strong. No strain on the surface by the feed. If the feed goes out to is supported by arms that come out to the side, when it's tipped over, it's going to change its shape. Even some of the big guys have that trouble. But there's no need to have something out there if you do it properly. And let's do it properly first time. Feed access, I've mentioned that briefly. Smaller F over D for GT. When I built my first dish, a 2 dB preamplifier was a pretty good one, and really the dish noise didn't come into effect. These days, we know the preamps have gone down, and our antenna is becoming a more sensitive, more noisy part of our system. And the other one's auto track, which I'll talk briefly too about that later on. So they're my design factors. There is also one extra one which I haven't put in there, and that's to have the transmitters remote from where you want to work and receive things. Most people have a high bounce transmitter, even if it's a solid state, when it makes some noise. So in my case, I've got that out of the shack. It's over near the aerial. My hub, unfortunately, I didn't have any scrap aluminium on my farm, but I did have a little bit of scrap steel. And so my hub is made of water pipe, quite a solid central tube or stress tube. When I made this up, I couldn't get the surface of my circular pipe level. There was little bumps in it. I wasn't perfect. But by putting these little adjusters on here, and I'll talk about them later on, I could get the surface within 1/4 of an inch of what it should have been, or hopefully less. To hold the feed, I built a backing feed arm, which is supported by the central hub, and it comes out to the side, and my feed comes up in that angle. So on the actual ribs, all the ribs have to do is support the mesh and don't have to support the feed. Here is the feed wound down. Now when I say wound down, back here there's a winch, and out here there is some cabling in a pulley system so that I can actually wind that up into the operating position and wind it down to walk up to the feed to do anything I wish to do to the feed. So in this case, there's a few ferns here. There might be an odd little rock, but I'm not up a ladder, I'm not up a tower, I'm down at ground level. And I think we all know about this. My old dish, where's that little button? Over here. I've used the same feed in my new dish as I used in the old dish. And I think I've got the circularity right. But the noise figures have come down and it's changed the situation. Absolute encoders. In this case, inside there, we have a chip sitting over, a magnet sitting over a chip. When my friend put the thing together for the tracking, I said to him, well, that's too simple, it won't work. But we hooked two of these encoders together and we could only get 0.8 or 0.5 degree difference between the two. So I think the accuracy is good enough. Since then, there have been quite a few encoders come out commercially. How strong that has to be? Well, fortunately, that's not my system. But in my case, I had surplus steel on the farm and I sourced a few other little bits and pieces. But I guess it's strong enough, as it stood a 110 gale not too long ago. There's my Azimuth platform with the elevation system. Whoops, gone too far. With the elevation system in place. And the little room here is my transmit hut. Back in behind here is where I run my hydraulic motor to drive it around. To drive it around, I do drive one wheel, and there's some rams to drive it over. Now this is where I was talking about putting the little, this is meant to be the top tube that goes around the hub. And to get the positioning right, these little spaces were either positioned on the top of the tube or down a bit, depending on the height of this tube. The reverse parabola was set up and these were adjusted to get the level pretty right. Okay, hydraulic motor, driving a worm drive to drive one wheel to turn it around. This is just a coupling. And there's two rams on the back of the dish to tip it over. The basic ribs were made out of inch tube. To actually hold them, I made a little plug, put it in the tube, that's threaded, and I welded this in with some eutectic welding rods to give it a strong grip on the centre and the outside rim. This was a little plate that went over those little plates on the centre. And these ties, they're commonly used in reinforcing rods in farming, in anyone doing building. And this tube actually twists them together. But in this case, they're stainless steel rods, stainless steel wires, and that's what holds the mesh on my dish. Home they're used in clay pots, but they do a pretty good job. Okay, pie sections, by cutting that piece up there and laying it on there, everything seemed to work out pretty flat. You can see that's a piece that's been put in there from the piece that's been cut off. And here you can see the ties that we had around the system to hold it on. And fortunately, the bigger dish you build, the easier it'll lay flat because the surface doesn't twist quite as much. Another winner for me was the bearings that hold the azimuth or the elevation are made out of wood, and there's one of these in the central part of the rotation system to hold it in place. In our country we've got red gum or jarrah. Perhaps some other countries mightn't be fortunate, would have hardwood, but I'm sure you can find some other material other than a steel bearing to do the job. Feed arm and focus. Well, I've talked about the feed arm, but this is up in situation. The real focusing effect, all I did was tip the thing, once the feed was in, tip it over, point it at the sun, and wind my little handle till I had maximum noise, and then I adjusted the angle so that it was pointing straight at the system. 5DJ, a very good friend of Doug, 3UM's, put the tracking system together for me, and this was one of the early two-line displays. It's basically a shack unit or a one board unit with one pick on it. It runs real time with a real time clock, and this is all you need to do to get the information as far as where the moon is or where the sun is. RS2 up to, for Cat5 cable up to an AS board, and this board is virtually the same board with a different chip in it for whatever encoder you might like to use. And if you have a look on John's website, 5DJ website, you'll find a bit more about that. You can also hook it into a computer and use Doug's 3UM's tracking system if you want to track anything else other than the sun or the moon. If you want to do some noise checks or other things, you can track it that way. I do have some boards and chips with me if anyone wants to a spare unit or putting in a new system. I think the basic kit, which contains the boards and the chips, is about €38, so it's not too difficult, not too expensive. With the new controller, we upgraded the screen. It gives you all the information you want to know. The main thing, I guess, is Doppler. You set the frequency, the Doppler will change, and the position of the aerial. To calibrate it, there's one little button up there that pointed at the sun. Get your maximum sun noise, click the button, and you're calibrated. Okay, that's what I started with. In this case, Eric 5LP had put the ribs together, but unfortunately he couldn't manage the rest of the system. Getting close to the final assembly. As you can see, there's no other houses near me. Pretty good area, but reverse parabola. I sometimes call that one how to shrink a ute because it makes the ute look small. And it's always good to have friends when you want some work to do, to put the mesh on. But that's my son in the middle and one of my other friends alongside him. We did it on a fairly warm day, but never mind, we got there. Lift off. The actual dish itself, in that situation, the crane driver told me it weighed 600 kilograms, and most of that is in the hub. As you can see, there's no actual feed arm. There's no feed arm support on that yet. We put that on after we put it up. First tip over, it's always a frightening thing whether you can tip it back up again. Because I remember when Doug put his dish up, he had to get the truck to pull it back up before he had counterweights on it. Feed arm installed, and the dish in the operating position pointing moon rise. But as I said earlier, that's where my transmit noise is. I operate down in a little shed there, and it's one of those things, when you tip the dish over, it seems to grow. Performance, I guess in the early days I was disappointed. I couldn't get the sun noise, I couldn't get echoes. All seemed to be working, but I had an unofficial guest. I had a bird that built a nest in my feed. And take the bird's nest out, half a bale of hay, and it all worked. Moon noise, I can see about that moon noise. And about that sun noise, they're not exact figures, but they're just what I can seem to come up with. I probably should be a little bit more on sun noise, but perhaps the sun wasn't as hot as it should have been when I measured it. A few acknowledgements. I guess my friend 5NC helped me with the engineering design, and that's mentioned in the story. And many other amateurs who have given me things over the years. And I'll let you read that for yourself. Okay, any questions?
Thank you, Chris, for your nice presentation, and I make sure to pay a visit to you next time I come down.
Chris, I will ask you a question, if I may, before you disappear. I wonder if you have actually pointed the dish at whatever noise source, not the sun, but some other, Cassegrain is too far north, I guess, but whatever you use in the south, and actually tried to measure your operating dish efficiency.
To be honest, no, I haven't. At this stage, I seem to be able to hear people that can hear me, so.
It's good enough, I guess, is the answer.
Good enough, yeah.
Anyone else? Okay, so last presentation for the day will be by Dave, G4HUP, Azimuth drive for small dishes. Here we are.
Good afternoon, ladies and gentlemen. Nice to see so many of you again. No, that's not mine. So, is this okay? Yeah, okay, that looks more familiar. Somebody read the proceedings yesterday. I think it was Mike from Japan. He said, that's not a drive system for small dishes. You can use that on much bigger dishes. He may be right. I like the line that Chris had in his document, which said, you solve the engineering problems of stress as you go along. So hopefully, I'm not expecting any stress problems with this. We'll see as we go. That is how I left it a week ago, which is way further on than the proceedings show. But we have actually now got the dish on the mount. So what I want to look at is how I've converted an X-satellite service, a head-end type dish for as an L control. It's the second time I've done it. I did it in 2006 with a 2.4 meter prime focus dish. This is the first time I've done it with an offset dish. And as Chris said in his presentation, this is not really about this is what I did. It's ideas for what can be done and the sort of problems that you face. So with the 2.4 meter prime focus, I'm just going to very quickly cover that. What I was provided with by the manufacturer was a frame on the top of the head post, and the elevation was through the middle of that frame. So the whole of that square frame elevated, and there wasn't really much room to do anything to gain azimuth. So a trip to a motorcycle shop got me a front sprocket and a rear sprocket from a motorcycle system with a chain, and I made a drive where this sprocket was actually clamped to the pole, and as the motor drove, it pulled this platform around the pole. The most difficult part was actually the bearing inside there, because these poles are not very good. They're not very round. They're off true. And it was actually quite difficult to set that up so that went smoothly round. That was one of the problems with the dish. The second one was that the guy who did the bearing for me didn't follow my instructions. He thought he had a better idea, and it just didn't work as well. But out of that dish, I had a number of contacts on 23 centimetres. The drive ended up taking about 70 seconds for a full rotation, which, standing there in the cold looking at it, seemed perfectly good enough. Real life, operating on 23, said it was much too fast. It was too coarse. By the time the controller had said turn the dish on to move it, and the dish had come on, it had gone too far. It didn't, it was constantly hunting. It wasn't good enough. And the other problem was that the W2DRZ controller I was using at the time was really running out of steam at 23 centimetres. Great controller for 2 metres. I had conversations with Russ and Tom, and they really did not understand the need for the ability to perhaps offset the dish a bit or control it. And there's actually been conversations with them on MoonNet recently, with exactly the same problem. And we're 10 years on. They're still trying to understand that problem. So, when I lived in Germany in the early 2000s, I managed to get hold of a 1.8 metre offset dish. It cost me €60, and it was brand new in the manufacturer's packaging. It was wonderful. It was too good an offer to refuse. And for 10 years, it's been parked behind one of my trailers, waiting to be used, so it's now been dragged out. It's only 1.8 metres, so it's no good for 23 centimetres really, but I'm intending to use it on 3 centimetres. So I need a very nice slow drive. It's a different structure on the pole. It has an axial bolt there, which secures the horizontal arm to the top of the head post. So it's a different mechanical problem to provide an azimuth drive for it. And the route I chose was to split the arm from the top of the post and put a gearbox in between, lifting the dish about 150 mm, about 6 inches for the metrically challenged, or 150 millimetres or so above the dish, above the head plate. First job was get on the computer, play with the CAD system and see what I could work out. Once I'd found a few bits, I found an 80-to-1 reduction gearbox. I found a nice big sprocket. So here would become the drive shaft for the dish, and here is the reduction motor with a drive in the side there. And I spent a little while dealing with that, decided to make it out of 6 millimetre instead of 4 millimetre plate. And it looked reasonably okay. So the first thing I did was test the design. MDF is a wonderful material. No good for the dish, but great for making sure everything works and fits. So I built a complete gearbox on MDF. These are the plates that I used. And here you can see part of the assembly. There's a worm drive motor on the side. Thank you, Johannes, OE5JFL, for pointing me to that motor. And an Italian gearbox, so it's very appropriate that we're presenting this here. A 20 millimetre diameter output shaft. And I built a complete working drive, no sensors, no control on it, thrust bearing on the top with a nice plate to take the head arm, and also the limit switches will be mounted on there. So I had the whole thing running. I was able to prove the design, find out where my CAD work was wrong, and I would need to change it before I cut real metal. And then we got down to cutting some metal. I had the outline of the plate laser cut to make sure that I had two plates exactly the same size. 6mm steel is not really the stuff to cut in the vise at home with a hacksaw. But then started to build the assembly up. Each corner has a large bolt with a sleeve on it to provide the spacing between the top and bottom. These 4 points, plus a plate on the side where the motor is, are the points that will take the whole weight stress of the dish down. So they have to be strong. No, oops, same problem as others. Where have we gone? No, there. No vertical stress is placed on the rotation shaft that goes in there. It's all taken by the frame of the dish. And there we have an assembly on the bench with the complete gearbox, with the arm on top. There's a plate here that bolts to the bottom of the arm, and the shaft goes up through the top there. There are 2 bearings, one on the bottom plate, one on the top plate, to keep this straight. Again, they take no vertical stress. All of that is taken by the thrust bearing and is transferred into that top plate. Here we're starting to add the sensors. This is the Azimuth sensor. It's a 1-to-1 toothed belt drive running a MAB25 sensor for the JFL controller system. And here's the limit switches. I have an operating paddle here and the 2 switches either side. Here is where I put my my connectors for oops, wrong one again. No, wrong way. There we go. Here is where I put all the connectors for the cable work, so I can just keep them a little bit drier than otherwise might be. Right. Finally, a mock-up in the garage. My wife is very pleased now to have her garage back again. This was there through the winter and until about 2 weeks ago. So now we have a lot more space in the garage suddenly. But it did enable me to work through the system, get a lot of things ironed out in here, get the elevation set up, and actually run the system off the controller just to check that it would all behave correctly. Here is my Dryax controller. It is still in the development or experimental stage, if you like. It needs to go in a box now, but this enabled me to run the system and have it under full control and make sure everything behaved correctly. Was able to check the tracking. And the end of last year, I put in the groundwork. I live in an area where we have heavy clay soil, and those of you who suffer the same affliction know that you have about 2 weeks in the autumn when it moves between being like concrete and like mud. Similarly, you have another 2 weeks in the spring. If you miss those, tough luck. Either way. I just managed to catch the autumn window. So a little bit of drain pipe work to get me a cable duct, and finally then assembling the system properly. Firstly, centering up the gearbox on the head plate. There are 2 plugs. Under that point there is a plug that sits into the top of the original bolt hole, and there's another plug at the back here that sits into a hole at the back of the plate, and they are to stop any twist or turn of my gearbox on top of the original motor plate. They locate in there. The gearbox mounting bolts go right through this plate and hold the whole thing in place. So then we could build it up in the workshop and put it onto the system. Here you can clearly see the 2 bearings. We have the drive shaft, and you can now see the chain tensioner on the back of the chain there. and the sensor system, all quite compact. These lugs on the side here are for locating some covers to keep the weather out. The 20mm shaft was a bit smaller than the original head bolt through the top there. So I had to make up 2 collars so that the shaft remains central. And then the whole system was put together. The elevation sensor is on the axis of the elevation. It's not a pendulum type. It's the MAB25 encoder. And there is a lever arm that is attached to the elevating spine. So as you take it up, this lever comes back and turns the encoder. I've used pendulum encoders before and seen quite a lot of swing on it as you step the dish. So I decided I would link it directly this time, and we'll see how that performs. In the background there, you can see the dish that will be going on there. And here we are. Sam and a couple of other local guys came and helped me to put the dish in place. It's a 1.8 meter offset. It's about 2 meters in that direction, and the F2D is about 0.65. So here the feed arm is in place, and that's pretty much where I've got to. I did have it tracking the moon and the sun for about 3 or 4 hours each, and it stayed in step, which is what I was happy to see. It was within the error band that the JFL controller is looking to keep it. The addition of some weatherproofing on the outside, and finally that point there topped off with the top of a jar of peanut butter. I was looking for something to put on there to just weatherproof the top of that steel shaft, and I happened to find one of those spare in the kitchen. So a bit of silicone sealant and a jar of peanut butter saved the day. I put rubber skirts around the sides and the front and back on there just to keep the weather out of the main shaft, but that is how we left it. What I have to do now is dress cables in and connect it back to the shack. All of my testing has been done with the Dry-X controller sitting on the floor with a power supply right by the dish. I need to actually check the sun noise and find exactly where the feed point is, and then all I need to do is the RF bit. Conclusions. I've had lots of mechanical learning points. I'm not a mechanical engineer. I dubiously claim to be an electrical and electronic engineer, but I'm not a mechanical engineer. Drive solutions are mostly individual. It depends what you get with the dish. If you're using a dish that a manufacturer has made, you're stuck with whatever he did. So you've got to try and find a solution to it. Just recently, I've acquired a 2.4 meter offset, so that's going to be the next gearbox type project, converting that to some Azimuth drive. I spent quite a bit of time getting backlash out of the system. I learnt to use keyways in the sprockets to make sure they stay in the place you think you left them. Otherwise, you come back and they've moved. And various things like that. Use bearings wherever you can. If there's a place where you've got a shaft going through something, stick a bearing on it. Tighten it down and put a bearing on it. Don't leave it just to go through, even if it looks like a nice fit. But all good fun, and hopefully somebody in there may find something useful for a dish you need to convert. Thank you very much.
Any question?
I'm happy to take any questions, but as it's the end of the day, I can appreciate you all want to be out. Yes, Al. Yeah.
1 second.
I guess this is more of a comment, but I've been using the W2 DRZ tracking system. I don't know what your experience back then, but I have a 28-foot dish. It's what tracks at 10 gigahertz. It amazes me. There is some playing with getting the right ratio between when you turn it on and you turn it off, but it's a little bit, it's part of the, there's problems in my own system. It's a little bit touchy because I got some slop in the thing, but it certainly tracks, and it does really nice job on 6 centimeters, and you know, we're talking about 28 feet. So I can certainly recommend it. I know there are a lot of other excellent tracking systems out there. My other comment, I can't help but say, why are you saying you can't operate in 23 centimeters with a 1.8 meter dish? There are a lot of people on.
I know there are.
Several,
Yes.
maybe I should say,
Yes.
who are quite successful with small dishes like that.
Yeah, no, I particularly want to get on 3 centimeters. That really is where I'm focusing on. Coming back to the comment on the controllers, my experience with the 7.2 meter dish at WC8 VOA a few years ago convinced me very strongly that you really do need to be able to offset the dish, especially on 3 centimeters. You are looking for not just moon noise, but optimizing moon noise on the moon at a dish that size, and I'm sure you find that on 28 feet as well. Yeah. Okay, thank you very much, ladies and gentlemen. Thank you. We'll do that.
Thank you very much for your contribution.
Thank you very much. Thanks. A real pleasure to have been here. So thanks for all your work. Thank you.
Okay, it seems that we made it through the day at least. What we are going to do is, if the light is still likely to be good, we could move outside, downstairs, I think, to take some pictures. Let's hope that only one will be enough, but we'll see. Okay, thank you, by the way, for the nice day, and see you later and at the gala dinner.